Hey everyone, welcome back. Today on the bench we're going to take a look at a curve tracer again. We've done a couple of videos on them, but this time I thought we'd build one. What I have here on the breadboard, disregard the little module in the back, is sort of the classic Octopus curve tracer circuit. You could find any number of schematics for these on the web, but there's one that is sort of most popular, and it's from an article that was done in the 70s, and it is based on this design right here. This is based on sort of a classic filament transformer, either a 6.3 or a 12.6 volt filament transformer. The original circuit was based off of a 6.3 volt transformer that's center tapped, and resistor R1 would have been 220 ohms. If you're using an actual 6.3 volt transformer, you would use a 560 ohm resistor in R1. And this is it. It's pretty simple. This design will limit the testing voltage to 1 volt RMS and to about 1 milliamp. And it was designed for in-circuit testing. So the idea here was that you could test components in circuit, test diodes, transistors, look for shorts and whatnot, with the circuit powered off, obviously, but without having to remove any components. The way that this works is for resistors R1 and R2 forms a voltage divider, and that drops our voltage down from 6.3 volts down to 1 volt. Resistor R3 is a current limiting resistor, and that limits our current to 1 milliamp. Disregard my beeping meter. And we've got our horizontal and vertical connections to our oscilloscope and our spot for our device under test. Let me just make sure this doesn't beep again. If we look at this little chart up here, we can see that for the classic Octopus, using a center tap 6.3 volt filament transformer, we would have used 220 ohm resistor. Gives us 0.98 volts out and just about 1 milliamp. If we use the full 6.3 volts, we would use a 560 ohm resistor. It gives us just under 1 volt and, an equivalent current out. And so right now, if we look at this circuit here, you can see that this is what I have on the bench at the moment. This is our 1K current limiting resistor. This is our 100 ohm second part of our voltage divider. And back here we have a 560 ohm resistor. And I'm currently testing, it's hard to see it here, there's a small little diode in here. And if we zoom back out, we can see the curve for the diode on the scope. If we look at the voltage right now, that is coming out of our transformer, we can see it's 6.48 volts. If we move to the other side here, we can see that voltage on the other side of the divider is 0.966 volts, so we're just at about 1 volt, and it works really well. So you can throw this together on a breadboard, no problem. The one issue with such a low voltage and current is while I can turn on this diode, which only has it turns on at a very low voltage. It's got a voltage drop of turn on voltage of 0.6 volts. If I go to test, let's say this red LED here, there's really nothing. If I turn up, let me see here, yeah, it won't turn it on. And I have another LED on here. This is a 2.7 or 3 volt LED, and it obviously won't test that. But for basic silicon transistors, other components, like I said, in circuit, you really need a low enough voltage and current that it doesn't turn on other devices in the circuit. So which is why it's designed as it is. So I have a section on here called Our Octopus. And our Octopus is based off of a transformer here that I got out of an old alarm clock. I salvaged a transformer from it. And I measured it at full output is 13.28 and center tapped is 6.68 volts. If we go back and look, that was without any load on it. If I look now with a little bit of load that's on here, it's showing 6.48 volts. So it's close enough to the filament transformer. We'll use a 560 ohm resistor for R1. Gives us 1.01 volts RMS out and 1.01 milliamps of current. So we're still in line with the original design for in-circuit testing. But since we have a full 13 volts that'll come out of it, I decided we can take this and enhance it a little bit with a range switch. And what the range switch does is switches between the 6 and the 12 volt windings, which in our case is, roughly 6.5 and 13 volts. And to drop the voltage down, since we doubled the voltage, I'm just throwing another 560 ohm resistor in parallel with the original one, which gives us 280 ohms of total resistance, which gives us a voltage out of 3.5 volts and a current of 3.5 milliamps. Let me zoom back in here a bit. So if I switch to the other winding here, I need a little something to help me pull this out of here. Come on. If I switch to the 13 volt winding, and if I toss another resistor here in parallel, and let's adjust these back down to 1 volt and 1 volt. So we see that I'm getting, this is 12.26 volts now out of the transformer. If we look on the other side of the voltage divider, we can see that we're at about 3 volts, 3.1 volts. So as always, anything with an unregulated supply, this is just a transformer. It's going to depend on what your actual line voltage is. Mine's about 123 volts or something, but that can vary. So we can build this on a breadboard like we did here, and it works well. And now with the higher voltage, if I go over, I can test. You can see the red LED comes on, and we can see that turns on at about 1.6, 1.7 volts. Just put my hand behind it. You can see that that's glowing. And I can even test this blue LED. Oh, I got that in backwards. Let's spin that around. There we go. And we can see that this turns on at 2.6, 2.7 volts, which is about right for this blue LED. So out of circuit, we could test some components that require a little more voltage, a little more current to do their thing. Let me back up here so we can show. There we go. That's the curve for the red LED. It's at about 1.7 volts, and the blue LED about 2.7 volts. This is great on a breadboard. You can throw this together pretty easily, clip a bunch of leads to it, test the odd component. But if you actually wanted to do in-circuit testing, this is not terribly convenient. What we really need is to build it into an enclosure that we can put some probes on, and that's what we're going to do. So I started that. I've got a show here. I did a little preliminary work. I'm using an outlet box, got from Home Depot, and I mounted some jacks and a switch and some labels on the front of this panel on top of the box. And so what we'll do is we're gonna take these components off of here, and we're gonna solder them up onto the back of this board and turn this into an actual piece of test equipment. So give me a few minutes and we'll take a look at how that looks when it's done. And we're back. So this is the assembled Octopus. If we take a look here, this is our Y channel vertical or current. This is our X channel horizontal or voltage out. We've got our 1K resistor here between ground and the vertical, as in the schematic. This here forms our voltage divider that we had. You can see for our two ranges, we have the center tap going here. We've got the full transistor going here. And this automatically, when we select that, we switch in the additional 560 ohm resistor in parallel. Paired with that drops us down to 280. Sockets for device under test, positive, negative. Again, transformer. Assembly is very non-critical. I kind of pointed all the stuff around here. Like I said, built it in this outlet box, picked up at Home Depot. It all fits in there pretty nicely. I just got this holding that cable there, and I have this little tab just as acting as a strain relief. And if we back out a little bit, and we just slip that in there. Screw those down. And we're done. Nice and self-contained. I didn't bother with a power light. I also didn't bother with a fuse. I mean, sure, technically it should be fused, but, you know, if I needed to build another one, I'd build another one. So, looking on the front, I just over-labeled stuff a little bit for the sake of here, but this is our horizontal and vertical axes. Horizontal tells us volts, vertical tells us current, device under test, and our switch for our 1 volt, 1 milliamp, and 3.5 volt, 3.5 milliamp range. So let's hook it up to the scope, and let's look at a few components here. So we'll look at some stuff out of circuit. Got my little test boards here. So we'll look at a couple diodes. Let's look at this diode here. Looks good. This next one I know is a Zener, but we don't have enough voltage for the back end, so let's turn it up. Now if you notice over here, you can just start to see it bending down there. I increase the sensitivity. So it's just enough to get it to start to turn on. Not fully in the Zener breakdown region, but you can tell. So I think this is, again, I think this is like a 5 volt Zener or something like that. So it's just starting to break down a bit that way. Silicon diode. Here's a Schottky diode. This turns on at a really low amount. We can if we zoom in here, we can see this turns on at just about 0.2, like 0.3 volts. And if we look at some LEDs, higher region, that's a red LED. One. There we go. It's red, that's yellow. That's a pink one. That's the blue one. And we can look at, here's a capacitor. I think this is a 10 microfarad. It's 100. And I think that's 1,000. And if we come over here, I've got a set of back-to-back LEDs. Go to the higher region here. Set this back down to 1 volt, but and I've got a capacitor across a diode here. So the little box works nicely. So let me see if I've got a circuit board here that we can poke around on to look at. That's definitely a capacitor. So there's a component down here. If we look, where did I see it? I just saw right here. This looks like a transistor. So let's see if we can probe that. This could be that there's a capacitor in circuit with it. Yeah. All right, that definitely. Yeah, this is actually a main board from an oscilloscope that I've been pulling parts off of. But, yep. Yeah, it's a capacitor nearby. But, definitely works. From a part standpoint, this really didn't cost me a whole lot of money. The switch I had, the BNC jacks I had, the banana jacks I had. I actually have, I keep a bunch of these around just because they're convenient. You know, I really didn't spend any money to build this at all. Like I said, the most expensive thing in here would have been the transformer, and I harvested that from an old alarm clock we had that died. I'm going to include links in the description for some good documentation. One of the documents that I'm going to link to is this. This is a Tektronix TR210 tracker. And what this is an actual Huntron tracker. It was made for Tektronix by Huntron to hook up to an oscilloscope and to do curve tracing, as they call it, analog signature analysis. The reason I'm including a link to this is because the instructions for using this goes into a lot of detail about how to analyze components in circuit. We get into semiconductors, shows basic semiconductor curves, shows what those curves will look like with resistors in series, shows Zener diodes, talks about transistors. It's just good. It's a good condensed manual. I'm also going to include a link to a document from Huntron themselves about doing component signature analysis. Yeah, but this is it. So this is our final build. It's pretty small and compact, and like I said, it's got 2 ranges, which is really more than enough for playing around and testing stuff. The low range you can use in circuit. And like I said, it was, I don't know, I mean, if you had to buy all the parts for this thing, it's maybe 20 bucks or something. You could probably harvest some of the resistors, maybe the BNC jacks, even the banana jacks from some old test equipment or something you have laying around. But pretty much a junk box build. All right, that's it for today. Questions, comments, please leave them below. Like and subscribe if you're so inclined. And I encourage everyone to build one of these. It was a fun little project. You know, the case is soft plastic, so it was easy enough to drill. The labels were just made with a label maker. Like, you'll be hard pressed to destroy it. This will probably outlive you, me, and everyone else. All right, that's it for today. Thanks for watching. See you in the next one.